So let me give you an update. So this video I just showed you, it's old, maybe, I don't know, 10, 15 years, I'm not sure exactly, but so the narrator was talking about a space telescope that was going to be sent up to detect planets orbiting other stars. And so she talked about they hope they'll be able to detect some. Well, I mean, the telescope has been up there for quite a while. I don't know if it's still up there, I don't remember, but they found hundreds of planets orbiting other stars. So that's quite amazing. I mean, when I was in college and graduate school, no one talked about, finding planets outside of, orbiting other stars. That was, people talked about it, but there was no evidence. But now there are, I don't know if they have 1,000 yet, but there's hundreds and hundreds of planets that have been discovered orbiting other stars. All right. Okay, so here's a completely different topic, which is going to be important again in the next chapter. Sorry, I'm going to say that a lot. So we talk about light, and the speed of light is lowercase c, and that is, so the speed of light in a vacuum, that's the important thing. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. Well, that's fine. But that's pretty fast, by the way. That's 671 million miles an hour, 186,000 miles a second. It's really fast. Now, if light goes through something else besides, not a vacuum, let's say water, the speed of light is less. Okay, so that's why you have to, when you say the speed of light is 3 times 10 to the 8th meters per second, you have to say it's in a vacuum because it slows down when it goes through something else like glass or water or something like that. So how do you discuss that? Well, here, this is how they do it. So this is called the index of refraction. And it's equal to the speed of light in a vacuum divided by the speed of light in something else, water or glass or something like that. So, this is always less than c. So therefore, this will always be greater than 1. Okay? So n, the index of refraction, is always going to be greater than 1. Okay, now let's go back to this. C, well, whatever. So we have, I keep calling F equals ma, right? So when light goes from a vacuum to air or glass or something like that, it's an experimental fact that the frequency does not change, right? So the frequency doesn't change. Well, this, it gets smaller, right? This decreases. So therefore, what has to be true about the wavelength? It also has to decrease. Okay? So here's a result. Sorry to say this. We'll use it next chapter. Oh, sorry. I'll get to the result in a minute. I just wanted to show you some values. So air, the index of refraction is almost 1. We'll just take it as 1. Water, lead sulfide, whatever that is, Anyway, different types of glass, okay? But this is what I wanted to show you. Okay, so what happens to that wavelength? It gets smaller. So this is the wavelength of light in a vacuum. Then let's say this is a piece of glass or something like that. So the wavelength inside the material, the glass, for example, the wavelength decreases, but the frequency doesn't change. So the wavelength in the glass is the wavelength in the vacuum divided by n. All right? So we'll use that. So I'll say it like this. The wavelength of light in a medium, water, glass, whatever, equals the wavelength of light in the vacuum divided by the index of refraction in the medium. That's going to be really important next chapter. So that's why I'm telling you about it. Well, there it is. All right. So, yeah, you'll use that. All right. Next unrelated topic. We want to talk about power and intensity. Power and intensity. So maybe you'll remember in Physics 121, we learned the definition of power. So power, energy transferred over time. And in Physics 121, I told you we're going to talk about power in Physics 220 and Physics 221 and all over the place. So I'm just keeping my promise. So power is energy over time. So the units are joules per second, which is a watt. So when you go to the hardware store and you buy a light bulb, you want a powerful, bright light bulb, you get one with lots of watts, lots of energy per second. Okay, intensity is power divided by cross-sectional area. And you're familiar with that. I mean, if I had just an ordinary flashlight and I shined it on the wall, let's say I had a flashlight here, shine it on the wall, and it lights up this large area, it's not very intense light, right? On the other hand, if I have a laser and I shine the laser, there's this tiny, tiny little spot. And so it's high intensity. And so, they use lasers to do welding and laser surgery and all sorts of things because they can get a very intense beam of light. All right? So power, energy over time, intensity, power over cross-sectional area. So watts per meter squared. All right. Now, oftentimes, we have what's called a point source of light or radiation or whatever. So you just imagine a tiny little thing that's emitting light or radioactivity or have a sound speaker that's tiny, a point source of radiation. And so this is the equation for the intensity of a point source. So again, intensity is power over area. And what's the cross-sectional area? Well, what's the surface area of a sphere, 4 pi r squared? So power over 4 pi r squared, but this is what's important, right? The intensity is proportional to 1 over r squared. That's the important thing, okay? So let's say you're in a hospital and you're visiting your grandmother and she has a radioactive implant in her body, which is a point source, right? And you don't want to get exposed to the radioactivity, so they make you stand a certain distance away. But if you double the distance away from grandma, then what happens to the intensity? It decreases by a fourth, right? Because 1/2 squared is a fourth. All right. Okay, so this is the important thing, all right? For a point source, intensity, power over 4 pi r squared. Now, for a wave, it's completely different, okay? So, and again, I guess this is what you want to remember. Intensity is proportional to 1 over r squared, where r is the distance from the point source to you. Now, for a wave, completely different. For a wave, the intensity is proportional to the amplitude squared. And we're going to use that next chapter. I'm not spending a lot of time on it, but anyway. All right, next topic. Next topic. We want to talk about something called the sound intensity level. Okay, so we're talking about sound waves now, right? And the intensity of sound. So for most normal people, the threshold of hearing is 10 to the minus 12 watts per meter squared. Now think about it, 10 to the minus 12, that's incredibly small, right? So that's when like a normal, healthy young person can just barely start to hear something. Okay, a quiet room, the intensity, 10 to the minus 9. That's still pretty small. Busy traffic, 10 to the minus 5. A rock concert, 1. The threshold of pain, 10. Okay, now, I mean, I don't really care too much about, I don't want you to know these things, of course, but here's the thing. Look at the range of these intensities. The threshold of hearing is 10 to the minus 12. The threshold of pain is 10, or 10 to the 1. So that means the range covers 10 to the 13th. Well, that's crazy, right? I mean, how do you deal mathematically with something that goes from 10 to the minus 12 all the way to 10. You know? I mean, you're not going to use a line. You're not going to use a linear. You're not going to use something like you see on a meter stick, a linear scale, because that'd be insane, right? These are just too small, you know? All right, so think of your math classes. How could you change, or what could you do to these numbers to get them to be reasonable, easy to work with? Something from 10 to the minus 12 all the way to 10 to the 1. What could you do? Think of high school algebra. Logs, right? Logarithms, okay? Logarithms. So this is what people do. So these are intensities. So they came up with a new term. It's called the sound intensity level. You've heard of decibels, right? So this is decibels. Okay, so this is what they do. So the sound intensity level, beta, I don't know why they call it beta, but who cares? Sound intensity level beta equals 10 decibels. So that's the unit. It's the unit for the sound intensity level. So beta is 10 decibels times the log of I, or whatever, divided by the I0, where again the I0 is the threshold. Okay? So rather than dealing with these crazy small numbers, you can just work with this beta and its more reasonable numbers. Okay, now here's what I want you to do. So you have the formula, and you have everything you need up here. So please calculate beta for the threshold of pain. So figure out what beta is for the threshold of pain. So pause your video and use what you need to do and figure it out. All right, we're back. Okay, so again, beta equals 10 decibels times log of I over I0. Now, what we want to do is we want to calculate beta for the threshold of pain. Well, for the threshold of pain, I is 10. So it's 10 watts per meter squared. And I0 is 10 to the minus 12 watts per meter squared. So 10 is 10 to the 1. So what's 10 to the 1 divided by 10 to the minus 12? It's 10 to the 13. So this is 10 decibels times log of 10 to the 13. And what's this? What's the log of 10 to the 13? Well, that's the same thing. All right, so log of 10 to the 13. Remember your high school log rules. You put the 13 out in front. You get 13 log of 10, and this is log base 10. So what's log base 10 of 10? It's 1, so it's just 13. So this is 13, and so you get 10 decibels times 13, or 130 decibels. Yay! All right. All right? Okay, that's not super crucial, but there it is. Okay, the next random topic, which is really important, so we're going to slow down here. And I guarantee you're going to have a question on the next topic on your exam. The next thing we want to talk about is called the Doppler effect. And that has to do with the relative motion. How many minutes have we gone?
We've gone 30 minutes.
So let's stop.